I'd like to introduce you to two ideas about how we can transmit digital information, the very basic first concepts that we'll be seeing in much greater depth. So I'm going to be talking to you about pulse-coded modulation versus pulse amplitude modulation, which are known by the common acronyms of PCM and PAM. This information is covered in section 2.4 of the textbook for the course from Scholar. So first, let's start with a little bit of vocabulary for digital communications. There's three important concepts. One is the bit, which of course is a binary bit, either a logical 0 or a logical 1. Then we'll get into something which is a symbol, and a symbol could cover, for example, a larger number of bits could be included in a single symbol. And when we discuss PCM versus PAM, that will give us our first opportunity to distinguish what the difference is between a bit and a symbol. And then we'll also have the vocabulary of an alphabet or constellation, and this is a collection of for example, the symbols. First of all, when we're talking about bit, the alphabet for bits would be 0 and 1. So the alphabet would have two entries in it, 0 or 1, logic 0, logic 1. We could have a tertiary symbol system where there are three symbols that might be sent, and we could call them ABC. And we'll be discussing what those symbols, how would we represent them when we're actually transmitting them. Okay, let's start off our discussion with a little vocabulary. So a bit, I think everyone has a very good idea of what is a bit. It's a binary symbol. It could be either a logic 0 or a logic 1. So other than a bit, we can expand this idea to be a symbol. So digital communications means that there is a countable finite number of symbols that can be transmitted, or logical values that can be transmitted. So in the case of a bit, it's binary, there's just two. But we can expand this idea and think about symbols. So the third one is called an alphabet, and that's kind of the collection of all of the symbols that we're going to be using inside of our transmission system, our digital communication system. So an alphabet is a connection of what we're going to send. So let's get some easy examples. Binary. A binary alphabet. What does that look like? Well, that of course is typically, we use 0 and 1, logic 0, logic 1, to represent the binary. These would be individual bits, the collection would be the alphabet, and later on we'll see why we call it constellation, because we'll actually have a geometric way of representing these. But for now, let's just continue on with maybe a tertiary example, so three-level alphabet. And you know, we could give them any names we want, A, B, C, or something else. So it's not important. The idea is it's a collection of discrete digital versions that we're going to be transmitting over our communication systems. Okay, so that's a little vocabulary. Now let's give some context. So there's a couple things that could happen. For instance, I could start with what is digital data. I could have a file which is saved in some ASCII form or something that's already digital. But it's possible that I'm going to be transmitting information over my digital communications link which starts off as analog. For instance, voice. If I'm going to transmit voice over a digital communication system, well, first that voice has to be digitized. It has to become analog, digital. So we could start with analog, and then of course we're going to have to convert it and go to something that's digital. Okay, now you would think, fine, now I'm digital, now I've got to transmit it. Well, actually, I organize my information in a digital format. But when it's time to do the transmission, I have to put it back into analog, right? I have to either send a voltage or send some light, or depending on what my communications media is, if it's a fiber link or a free space visible link or a wireless RF link, maybe I have to send a carrier. So there's all kinds of different forms it can find, but finally I have to put it back to analog when it's actually going over the air. So these are a couple of the ideas that we're going to be seeing in this very little introductory section where I talk about PAM and PCM. And so when I talk about these, I'm going to start out my discussion talking about how do I get from analog to digital. So how do I go from an analog signal like voice into some sort of alphabet where I've divided things up? How do I do that? And so that's kind of straightforward. And then I'm going to talk about this other transition from digital to analog. And so this is going to be a discussion of what we call line codes and waveforms. What waveforms can we use to represent these concepts, these digital representation of the data. And I should say that the last part, which is where we go from digital back to analog, we sometimes call that a waveform. So that's like one of the ideas we'll be seeing later on. So, the first part, the first conversion from analog to digital, assuming I have an analog channel, something like the voice. So we know from our study of Fourier analysis that there is something called the sampling theorem. And if we sample fast enough, so if I take my voice as I'm speaking and I sample it and take values of it discrete at certain points in time, so it doesn't become a continuous time signal, but I get discrete samples of that signal, that I can have perfect reconstruction, theoretically at least, if I sample fast enough. Okay, so suppose I've sampled fast enough. I can do perfect reconstruction, but of course that assumes I have infinite resolution of that sample. And when we transmit information, we're not going to be able to have infinite resolution. In fact, that's going to be one of our design choices, would be, how much resolution do we need in order to have a good recovery of the original signal. So all of these issues are a little are addressed by a device that we call an analog to digital converter, or an ADC. And ADCs are practical circuits, and of course they'll have some finite resolution, and they'll also have some finite bandwidth. And so sometimes when I'm discussing throughout the course of digital communications, when I talk about the bandwidth of the channel, part of that is going to be the components I use for my system. And if part of my system is converting from analog to digital, I'll be using a device such as this, and it has a certain limited bandwidth, which I'll have to respect. And if I don't respect it, then there'll be some effects that I'm going to see even in my my eventual reconstruction. So this is part of it. But this concept, I think, is clear enough. Let me just step you through some of the other issues. So there's the digital part. Now, suppose I've taken this analog and I've used the sampling theorem and I've come up with some finite resolution, and so I end up putting this analog continuous time signal into a digital sampled form. So now when it's time to take this digital data and to actually transmit it, as I mentioned, the signal is actually going to be analog during the transmission through the channel. So whether that's light on fiber, whether it's a voltage on a wire or a cable, coaxial cable, or whether it's an electric field which is propagating wirelessly, all of these cases, the media is actually taking my digital data and transporting it on some analog form. So the transmitter will involve some digital to analog converter, another circuit that comes into play when we're in a digital communication system. So a lot of these concepts, for the rest of the course, we're just going to idealize them and assume that they've happened in the background. So in the beginning of the course, I'd like to give some context on some of these assumptions that we're being made, and to remind you that there are components involved that will impact the performance of communication. So, for instance, the digital to analog converter. Now, I'll have a choice of what kind of symbol waveform. Remember, I said that the symbol of whether a bit is a subset of a symbol. So when the symbol has to be transmitted, we'll be talking in this class about what would be interesting waveforms. What would be a waveform that would, have some characteristics which were desirable in the communications environment. So that'll be an important part of what this course is covering. And also, finally, of course, this DAC component, digital to analog converter, just like the analog to digital converter, has finite resolution and bandwidth issues. So again, these are just realistic components. We'll always have some limitations that we often deal with in the abstract. So let's go back. So we've seen the analog to digital and the digital to analog, two different parts of this communication system. So here I'm assuming that I have some continuous time signal analog signal like the voice, and I'm going to have to use some device, some sampling device, some analog to digital converter, which is going to sample it. And of course, depending on the circuit that I use, there are different kinds of sampling ADCs. Let's take a couple issues that come up when I'm using these devices. So the easiest idea is the idea of quantification. So that I'm going to have a finite resolution, and how do I take a sampled version of this analog continuous time signal? So here's an example, this very easy waveform, which is sampled regularly, and we assume that it's sampled fast enough that we're going to have a fairly accurate reproduction of this signal once it's been transmitted. And of course, what we call first is the natural sample value, and that's the specific value of the function at this sampling time. So here we've got 1.3, at this point it's 3.6, 2.3, etc. So we have to, first when we're doing the conversion from analog to digital, we have to quantify it. So we have to give it a value from a restricted palette. So in this case, we've taken all of the possible values of our x of t, our waveform in the time domain, and we've divided into intervals where it's about, in this case, 1 volt apart. So for instance, between 3 and 4 volts, we have a nominal level of 3.5. So anything that actually falls between 3 and 4, we're going to call it a 3.5. So here it's 3.6, but when we have the quantized sample value, we'll see a 3.5. So here on the quantized values, it's always one of these points separated by 1 volt and centered around a half a volt. We can see here the different quantification levels, and as we sample, as we go along this waveform, we see here what are the quantized values. Okay, now I've got the quantized values, and what I should do is create something that I like to call a code book. So it doesn't really matter, is this, is it voice, is it something else? So when I'm sampling it, it could be volts that range from 100 volts to minus 100 volts, or it could be from 10 millivolts to 12 millivolts. I don't know what it is, but it's not really important. The important thing is here I've got 8 levels. I've got 8 levels that I have defined, and there is some value associated with it. So I give each one of these intervals a name, a code, and that is what is actually transmitted by my digital information system. And then when I get to the other end, then I can reinterpret these code numbers to be certain voltage levels. So that's an abstraction, if you will. So first of all, we take the sampled quantized value, and then we'll look up and we'll say, well, 1.5, I called that code number 5, and then 3.5, I called that code number 7. And so what I'm going to transmit in my digital communication system is I'm going to transmit the code 5, followed by code 7, followed by code 6, followed by code 4, and then when it gets to the receiver, they're going to interpret that as, oh, that's 1.5, 3.5, 2.5, etc. Okay, so now we have this idea of a code book. But now the question is, what do I really transmit on that digital to analog? When I go back to analog and actually transmit a waveform, what waveform am I going to transmit? Well, I have a couple options, and that brings us to the discussion of PCM and PAM, and that I started this section with. So let's start with PCM. Pulse code modulation, pulse coded modulation, whichever. So I have 8 levels, so suppose I represent it in a binary alphabet, and therefore 8 levels. I'll need 3 bits in order to represent or distinguish between each one of these different possible code numbers. So code number 7, I give it the 111. So it's a pulse that's coded. It's binaries. So I get 111. That represents a 7, and then I just count down in binary and just arbitrarily assign 3 bits to each one of the possible quantization levels. So if I'm using PCM, then what I'm actually transmitting over my digital communication system is logic 1, logic 0, logic 1, logic 1, logic 1, logic 1, etc. And then, of course, at the receiver, it's interpreted to recreate this analog signal. Now, that's one option. There's another option I could use, and that is to think of amplitude, pulse amplitude modulation. And that is to just assign different amplitudes to each one of the quantizations. And so, for instance, I might do plus and minus 1, might be something interesting. And of course, plus and minus 1, the difference between those is 2. So if I wanted to get another level, and I wanted it to have the same distance apart, I would take 1 plus 2 and get 3, minus 1 minus 2 get minus 3, and proceed in that way until I get amplitudes, plus and minus 1, plus and minus 3, plus and minus 5, plus and minus 7, until I get enough to cover the number of codes I have. And in this case, there are 8 levels, and so I have 8 different amplitudes, each equally spaced from the nearest neighbors. So this has desirable attributes, which we'll learn more about. So this is very common, and we give this a name. This is pulse amplitude modulation. Now, if I take this exact same analog signal and I want to transmit it with pulse amplitude modulation, no problem. I'll send amplitude 3, followed by amplitude 7, followed by amplitude 5, amplitude 1, amplitude minus 1. So I have these 2 options that I can use. I can use PCM and send a sequence of bits, or I can use PAM modulation and send different amplitudes. Real simple choice. They're both digital. In this case, I'm talking about bits, and there's a binary alphabet of 2. Now here I have a symbol rather than a binary bit, because there are 8 of them. So my alphabet is of size 8, and here are the 8 values that are the discrete levels that I could transmit. So these represent our symbols. So now we have a good example of symbols versus bit. And I want to start out, like very early in the course to show you the kinds of intuitions we could get very soon with some basic concepts that we have seen before in Fourier analysis above all, to understand, what would be some consequences of this very simple choice between PCM or PAM. So let's look in the time domain at a typical PAM signal. Now, before I showed 8 levels, make this a little easier, I'm just going to show 4 levels. So there's plus and minus 1, plus and minus 3 are the 4 levels that are possible. And in this case, I'm going to assign them a name in binary also. For instance, I could call the plus 1 level, I could call that a logic 1-1. That's what I do here. And the plus 3 level, I can call 1-0. So it's just another name. It's like if well, we'll just leave it for that. So I've given different kinds of names. It's either the amplitude, which is the physical voltage that's being sent. So during this interval, I send voltage level 1, voltage level 3, minus 3, minus 1, etc. So this interval right here, this interval of time, I call a symbol time. That's the duration in time that my symbol level lasts. So I say I'm going to send one symbol by the other. We can think of it as sort of being representing this time between samples. But in this case, it's actually the time between transmission. I send a symbol for a certain interval of time. So that's how I do it. Now suppose I have this exact same information, and now instead of sending the amplitude level, I take this binary representation, and instead I send a sequence of binary bits. What would that look like? Well, if I sent a symbol of binary bits, like this one I said was 1-1, so I'd have 1 and 1, and then this one was 1-0, so I'd have a 1 level followed by a 0 level. This is 0-0, etc. And so I would have just 2 levels. In this case, it's 1 volt or 0 volts. And there's only 2 levels, so it's binary. But if I want to send the exact same information, if I want to represent this waveform, which was sampled at this sampling rate, and at a given time of a sample, I either send 1 symbol, or I send, well, this is 8 levels, so there's 3 bits, but in the example here, it's 4 levels, so there's 2 bits. So that means if I want to send the same information in the same amount of time, I'm going to have, in the case of 4 levels, twice as many transitions. So if I look at the time of the symbol for PAM, it's this wide, but if I look at the bit period for PCM, that bit period would be half as long. So it's much quicker in time. So when we have a faster modulation. You know, there are more transitions in the red than in the white. When I have more transitions, what does that mean in the frequency domain? Well, in the frequency domain, faster, shorter pulses take up more bandwidth. So, PCM takes up more bandwidth than PAM right away. We haven't really studied anything about digital communications, but already we know that if we have these two choices, do I use a binary, two-element alphabet, or do I use a larger alphabet? Well, the impact is going to be on the bandwidth occupied. And bandwidth occupation is a very, very important feature of communication systems. So that was my point now, is to just give you this feeling for how choices on waveform can have an impact on the performance or the characteristics of the digital communication system.